Good morning. I am Dr. Niti Maheshwari, Assistant Professor, Applied Science and Humanities Department, Ajay Kumar Garg Engineering College, Ghaziabad. In my last lecture, I was discussing about polymers, which is the module 5 of the syllabus. And I started with the classification of polymers, how differently we can classify them. And today I am going to discuss about some of the important polymers, their preparation, their properties and their applications. And the first important polymer, it is a rubber, and it is Buna S. Buna S, it is also known as styrene butadiene rubber, which is SBR, and it is also known as government rubber styrene, that is GRS. Now, this Buna S, it is prepared by the random copolymerization of a mixture of butadiene and styrene in the ratio of 3:1 by weight in the presence of an peroxide catalyst. And this reaction, it is carried out at 5 degrees centigrade. Therefore, this Buna S, it is also known as cold rubber. Now, here I am showing the preparation of Buna S, where I have taken the monomers, the two monomers from which the Buna S is made. It is 1,3-butadiene and styrene. Both of these, they undergo polymerization, free radical polymerization in the presence of peroxide, and results in the formation of Buna S. Now, coming to the properties of Buna S, this Buna S possesses high tensile strength and it can be increased to 250 kg per centimeter square. This Buna S, it is also resistant towards heat and aging. That means it can withstand high temperatures, as well as we can use it for a longer period of time repeatedly. It will not age easily. Then this Buna S, it has high abrasion resistance. By saying abrasion resistance, I mean that its surface will not wither off soon, but we can use it for a longer period of time. So its surface is abrasion resistant. And this molecule or this polymer has high load bearing capacity. That means we can put high load on it, even then the properties won't change. Coming to the disadvantages of Buna S, this molecule, it can be easily attacked by ozone molecule even in the presence of air. And Buna S, it can be spoiled by oil and solvents because it has a tendency to get swelled up in the presence of oil and different solvents. Next, the applications of Buna S. Now, since it has high load bearing capacity, therefore this Buna S polymer, it is used in the motorcycle and the scooter tires. It is also used in car tires, cycle tires and tubes. This Buna S, it is used in conveyor belts. Then in the footwears, in shoe soles, it is also used as electrical insulator and as adhesive. By saying adhesive, I mean something which can bind two different surfaces together. The next molecule I am going to discuss is again a rubber, and this rubber is Buna N, which is also known as nitrile rubber, NBR. Now, it is also a commonly used elastomer. Elastomer which has a tendency to get stretched, and after I release the force, it will come back to its original shape and size. So this Buna N, it is a natural or synthetic material, and it does not break when stretched and when stretched, and when I release the force, it returns to its original length. As I have already said, it is also known as nitrile rubber. Now, this Buna N, it is a synthetic rubber copolymer of acrylonitrile and butadiene. That means the monomers of Buna N, they are acrylonitrile and 1,3-butadiene. Now, so the Buna S, it is prepared by the copolymerization of 1,3-butadiene with acrylonitrile, again in the presence of a peroxide catalyst. So here I have taken 1,3-butadiene and this molecule CH2 double bond CH-CN, it is acrylonitrile. They both undergo copolymerization and this resulting molecule is Buna N. Now, this Buna N, it is resistant to oil, it is resistant towards fuel and other chemicals, and which also means that Buna N, it has the higher resistance to oil, but flexibility of the material is less, it is less flexible. Then it is resistant to aliphatic hydrocarbons. We have a polar group. You can see here this CN, it is a polar group which is present. Therefore, this Buna N, it is resistant to aliphatic hydrocarbons. Buna N, it possesses high tensile strength and again it is possess excellent abrasion resistance. The surface does not wither off easily, so it is abrasion resistant. But this Buna N, it can be attacked by ozone, ketones, esters and aldehyde. That means those groups which are polar in nature. Now, Buna N, it possesses low resistance towards ozone, sunlight and weathering, as the double bond which is present in the butadiene segment of the chemical backbone. So, the weaker point is the presence of the pi electrons in the butadiene backbone. Buna N, it is more heat resistant. I can use it for high temperatures and it is not resistant towards different solvents. Coming to the applications, this Buna N, it is used in automobile parts and aeronautical industry. It is used in the automobile parts and also in the aeronautical industry. It is an ideal material for the aeronautical application, as this Buna N, it can withstand high temperature range, that is minus 40 degrees centigrade to 100 degrees centigrade. Then Buna S is also a useful material for disposable lab, cleaning and examination gloves. So, I can make different types of gloves from this Buna N. It is again used in the conveyor belts. Then it is used as lining of the tanks and as gaskets. By saying gaskets, I mean gaskets are something made up of a rubber, circular rubber, and they are used for the sealing of two metallic surfaces so that the air does not pass out of it, just like in the case of pressure cookers. Then this Buna N, it is also used in printing rollers, and XNBR, it is specially used for the modification of adhesives and epoxy resins. These are something which we use in binding of the two surfaces. So, Buna N is also used in addition with these adhesives and epoxy resins. Next polymer which I am going to talk today is neoprene. Again, neoprene is rubber. Now, this neoprene, it was invented by DuPont scientists in the year 1930, and the first name of neoprene was Duprene, and it is a synthetic rubber. This Duprene, it smelled bad and it was expensive, and it is produced by polymerization of chloroprene. This molecule chloroprene undergoes self-polymerization to form neoprene. This neoprene, it has good chemical stability. Coming to the preparation, neoprene, which is 2-chloro-1,3-butadiene or polychloroprene, it is formed by free radical polymerization of chloroprene. Now, this 2-chloro-1,3-butadiene is chloroprene. When it undergoes polymerization, it leads to the formation of neoprene. Now, during polymerization, these double bonds, they open up, there is a shifting of double bonds. As a result, the double bonds come in the center and there is a position for two new bonds at the corners. Therefore, the chain elongation process can take place. Now, coming to the properties of neoprene. This neoprene, it is a solid rubber material and it has different qualities, or you can say it has good qualities. This neoprene, it is again, it shows resistance towards oils, towards chemicals, towards ultraviolet light, ozone and many other general weather conditions. It is a strong and robust material and it can resist abrasion and can withstand temperatures ranges between minus 35 degrees centigrade to 125 degrees centigrade in certain cases. This neoprene, it displays outstanding physical toughness. It is a tough material and it is more resistant towards burning than any other type of rubber. Among all other rubbers, it is more resistant to burning. Coming to the applications of neoprene, this molecule or this polymer, it is used as wire and cable insulator. It is a rubber. We know that rubber is a bad conductor of electricity. Therefore, it is used as wire and cable insulator. Then it is used as bridge bearing pads. It has high tensile band, it is used for the preparation of high tensile bands for athletic stretch. Then it is used in high pressure gaskets. Then it is used for skin diving wetsuits in the water sports wear, where the water is not absorbed by the material. Then nylon, it is used in nylon laminated for all sorts of consumer items. Then again it is used as gaskets to seal water, air, dust and other environmental items. And in the case of automotive gaskets and in athletic equipments. So here I am showing different applications of neoprene. This is a laptop sleeve which is made up of neoprene rubber. Then the wetsuits, this is a small boat, and the boots, they all are made up of rubber. Now, the next molecule that I am going to discuss today is nylon 6. Now, this nylon, group of nylon, it represents those polymers which are made by the condensation reactions between amines and dicarboxylic acid. So, on reaction of acid and amine results in the loss of water molecule. As a result, amide linkage CONH bond is created between different molecules. So, those elongated chains which contain CONH group, they are given a general name as nylon. So, first nylon that I am going to discuss today, or the polyamides, the first nylon that I am going to discuss today is nylon 6. Now, this nylon 6, as I have already said, has an amide linkage and it is a resultant of polymerization between diamines and dicarboxylic acid. So, coming to the nylon 6, this nylon 6, it can be prepared by two different methods. First is by self condensation of eta aminocaproic acid. This molecule H2NCH2 5C double bond OH, this is eta aminocaproic acid. This molecule undergoes self condensation and it loses water to form the resultant polymeric chain of nylon 6. So, as a result, NHCH2 5CO N, this nylon 6 molecule is generated. And the second preparation is by the ring opening of caprolactam. Now, here this caprolactam, it is a 7-membered ring having the NHCO bond. It hydrolyzes to form, it hydrolyzes and the ring opening takes place and results in the formation of aminocaproic acid. And this aminocaproic acid, it undergoes polymerization. It undergoes polymerization by the loss of water molecule and results in the formation of nylon 6. So, this is the end product which is formed from the caprolactam. Now, the preparation, nylon 6 preparation begins with the caprolactam. It is a natural polypeptide more closely to caprolactam that would become an amino acid if it were hydrolyzed. If I hydrolyze the product, then I will get the amino acid. So, when caprolactam, it is heated at about 533 Kelvin in an inert atmosphere of nitrogen for about 4 to 5 hours, then the ring breaks down and it undergoes polymerization. That means we require high temperature and longer period of time for this caprolactam to open the ring and form the product. Then the molten mass, it is passed through spinnerets. Spinnerets is a goal structure, a round structure having small holes, and when we pass through these, and if I stretch the threads, then I am going to get the nylon threads from the spinneret. So, I pass through the spinnerets to form the fibers of nylon 6, and during polymerization, the peptide bond within each caprolactam is broken, and the active groups, they are present on each side, reforming two new bonds as the monomer becomes the part of the polymer backbone. So, the functional groups which are present, the active groups are the functional groups, they reform themselves so that there is a place for two new bonds to be formed, and they themselves become the part of the polymeric chain. Coming to the procedure, we take around 10 gram of eta caprolactam in a 25 ml beaker, and I use a small glass rod and add a small piece of sodium which is pressed into the caprolactam. The melting of the mixture occurs with reduced burner flame. So, I melt the mixture, and afterwards the liquefied material, it is heated to boiling. The deep brown molten mass, it is cooled down for 5 minutes. After cooling, as the cooling starts, the mixture will become more and more viscous. So, the mixture start becoming viscous, and the fibers, they are drawn by dipping the glass rod into the polymer and rapidly drawing out the solidifying material of the beaker. So, before it dries out or solidifies, we pull out the threads or the fibers of the polymeric material. Now, coming to the properties of nylon 6. This nylon 6 possesses high tensile strength. That means it can be stretched without deforming. It has high chemical resistance, high mechanical strength, and it is also heat resistant. We can see the process is easy, therefore it is easy to process, and it can be dyed easily. That means we can give different colors to it. Now, coming to the mechanism. The induction of the lactam polymerization, it occurs in 2 steps. Now, first, the caprolactam reacts with sodium. This is the eta caprolactam. It reacts with the sodium to form the lactam anion. And in the second step of the initiation process, this lactam anion, it attacks the another molecule of the caprolactam and it adds to it. When it adds to it, the ring adds to it, this molecule, it opens up. So, the molecule opens up because this anion, it attacks at the carbonyl carbon, and it leads to the ring opening and the formation of N-caproyl caprolactam anion. So, N-caproyl caprolactam anion is formed. This anion, it attacks the carbonyl group. As a result, this bond break and the ring opening takes place, and this molecule gets inserted here and a new anion is formed. The process repeats itself. Again, this anion will attack a new molecule and the chain elongation will take place. So, the another species is generated that can react again in the same manner. This happens over and over to produce a long chain of the purlon. Now, coming to the uses, this nylon 6, it is used as threads in the bristles for toothbrushes and surgical sutures. Then, it is used for the strings or for acoustic and classical musical instruments like guitars, like violin, like violas, like cellos. So, the strings, they are made up of nylon 6. Then, it is also used in the manufacturing of a large variety of threads, ropes, filaments, nets and tire cords, as well as they are used in the hosiery material and the knitted garments. Now, this nylon 6, it can also be used in gun frames which are made with a composite of nylon 6 and other polymers. So, it is in mixture with other polymers, it is used for making of gun frames. Again, it is used in the textile industry, in the carpet industry and for outdoor clothing, that is for the making of tents, backpacks, etc. The next polyamide which I am going to discuss today is nylon 6,6. Now, this nylon 6,6, it is a condensation product, and this condensation product, which is formed by the reaction between two different monomers which are hexamethylene diamine and adipic acid. So, the two monomers which are involved in this polymerization, they are hexamethylene diamine and adipic acid. Both of these have two functional groups, that means they are bifunctional in nature. And when two bifunctional monomers they react, they lead to the formation of a straight chain polymer. So, both of them are bifunctional, that is their two ends are reactive. Both of their ends are reactive and each end contains the same functionality. The other name is polyhexamethylene adipamide, poly-N-hexamethylene adipene diamide, maronyl ultramid zytil. These are the commercial names for nylon 6,6. Now, this nylon 6,6, coming to the preparation, it is a copolymer of hexamethylene diamine and adipic acid through condensation polymerization. And the name condensation polymerization has been given because in this process, simple molecule like water, it is released. Here I am showing the reaction. This is the adipic acid, CH2 whole 4 COH, COH and CH2 whole 6 NH2, NH2, hexamethylene diamine, and this is adipic acid. They react at high temperature, that is around 553 Kelvin, and at high pressure they result in the formation of the molecule which is nylon 6,6. So, the polymer nylon 6,6 is formed. So, this is the molecule nylon 6,6. The name 6,6 has been given because both of its monomers have 6 carbons each. Coming to the properties, now this nylon, it belongs to the family of plastics, and nylon properties include, it absorbs less moisture. So, moisture has significant effect on properties, and it is fair to easy processing. It possesses good physical properties, they possess good heat resistance, and they also possess good chemical resistance and extremely good wear and tear resistant. Nylon is not easy to break, and the price also is from moderate to high. Now, this nylon 6,6, it is frequently used when mechanical strength, great rigidity and good stability under heat is required. So, at high temperature, if we need good stability, rigidity and strength, then we use nylon 6,6. Then it is used for ball bearing cages, as electro insulating elements Then it is used in the pipes, profiles and various machine parts. In different machine parts also nylon is used. Other application, they are used as carpet fibers. They are used in airbags, tires and ropes, the nylon ropes or the nylon tires. So, these are the different applications of nylon 6/6. Here I am showing some of the diagrams where we use nylon as fabric, as plastic, as nylon rolls. Coming to the advantages again. Now this nylon, it has the ability to show luster, that means it reflects light. Then it can be semi-lustrous or dull, so its ability varies. Then durability, this molecule is quite durable. It is used for seat belts and it also has other applications. It has high elongation. It is again like other polymers. It possesses excellent abrasion resistance. Then it is resilience. Resilience is when we apply pressure, it gets deformed, but on releasing the pressure, it comes back to its original shape. So it shows resilience. It possesses high resistance towards insects, fungi and animals, then moths, molds, many chemicals. It is resistant towards the chemicals. Again, it is used in the case of making of carpets, stockings which are made up of nylon, and it melts instead of burning. It also has certain military applications like for the preparation of tanks, tents and the backpacks. Now these are the certain disadvantages of nylon, which is high moisture pickup with related dimensional instability. Then it requires UV stabilization. It has high shrinkage in molded sections, and high moisture absorptivity degrades the electrical and mechanical properties, and it is attacked by oxidizing agents like acids, like ozone. So it is easily attacked by the oxidizing agents. Then it is also attacked by strong acids and bases, and it possesses high notch sensitivity. Now the last polymer which I am going to discuss today is a polyester. A polyester which is made by combination of dicarboxylic acid or diacids and diols, that is dialcohols. So it is made by the combination of alcohols and acid, leading to the formation of an ester linkage in between the different monomeric molecules. So polyester today which I am going to discuss is the terylene or Dacron, or it is polyethylene terephthalate, which is PET. So polyesters, these are the produced by the polycondensation of dicarboxylic acid and diols. The molecule today under discussion is Dacron or terylene, or it is also known as PET. Now this molecule Dacron, it is prepared by heating a mixture of ethylene glycol. The monomers are ethylene glycol, which is OH, CH2, CH2OH, and terphthalic acid. The two acidic groups, they are at para positions in the benzene ring, then it is terphthalic acid, and the reaction takes place at around 420 to 460 Kelvin in the presence of zinc acetate antimony trioxide catalyst. And this Dacron fiber or the terylene, it is crease resistant. That means the material which is formed, it is not easy to put lines on it. It is crease resistant, and it is used with blending with cotton. So we can blend this polyester with cotton, then we can blend it with wool fibers, and it is also used as glass reinforcing materials in safety helmets. So here I am showing the reaction between ethylene glycol and terphthalic acid. The two are going to react with each other, and by the loss of two water molecules, it will lead to the formation of this molecule, which is Decron. So, this is CO, again there should be one O, CH2, CH2O and CO. Now, this Decron polymer, it is a very strong fiber and it will suffer very little loss in strength when wet. It is elastic in nature and it possesses the property of resistant creasing. That means you cannot set the crease in such materials. Then it can be set into permanent pleats when it is subjected to correct temperature. At the time of manufacturing, softening temperature, which is 69 degrees centigrade, and the melting temperature is 250 to 265 degrees centigrade, and the sticking temperature is 230 to 240 degrees centigrade, whereas ironing temperature is 135 degree centigrade. So, it shows good resistance to degradation by chemical bleaches and to abrasion. And the continuous filament yarn, it is used in curtains, in case of dress fabrics, in case of high pressure fire hoses, in men's shirts and in the thread, making of the thread. Now, this polyester material, it is not affected by moths. So, which is a worm for cloths. So, it is also blended with the other materials, so that the other materials do not get, especially wool, so that it does not get attacked by the moth and the wool becomes shrink resistant. Coming to the uses, now this PET, it is an excellent water and moisture barrier material. The plastic bottles made out of PET, they are widely used for soft drinks. Then PET sandwiches an additional polyvinyl alcohol layer to further reduce its oxygen permeability. So, on addition with polyvinyl alcohol, this PET reduces its oxygen permeability. That means it is not easily attacked by oxygen. And biaxially oriented PET film, it can be aluminized by evaporating a thin film of metal onto it to reduce its permeability and to make it reflective and opaque. And these properties, they are useful in many applications, including flexible food packaging and thermal insulation, such as space blankets. Now, because this PET molecule, it possesses high mechanical strength, therefore, it is used in tape applications, such as the carrier for magnetic tape or backing for pressure sensitive adhesive tapes. And the non-oriented PET sheet, it can be transformed to make packaging trays and blister packs. If crystallizable PET is used, then these trays, they can be used for frozen dinners, as they can withstand both freezing and oven baking temperatures. And as opposed to the amorphous PET, which is transparent, crystallizable PET or CPET, it tends to be black in color. And when filled with glass particles or fibers, it becomes significantly stiffer and more durable. Now, this PET, it is also used in thin film solar cells, and PET is also used in 3D printable thermoplastics. And one species of the bacterium in the genus Nocardia can degrade this PET with an esterase enzyme. That means I can biodegrade this PET molecules. And the Japanese scientists, they have also isolated a bacterium, Ideonella sacchinensis, that possesses two enzymes which can break down the PET into smaller pieces that the bacterium can digest. And this work can be completed in about 6 weeks time. Thank you.